Now, with reactions, there are 5 very basic types of chemical reactions that you should be able to predict the products for. And there's more than these 5 types of reactions in chemistry, but these are just 5 of the most basic types. And those types are synthesis reactions, decomposition, we have single replacement and double replacement, and we also have combustion reactions. And let's take a look at each one of these together. Before we do that, though, there's something that I just want to remind you, and that is your 7 diatomic molecules. So there are 7 elements on the periodic table that always come in pairs. So you might remember thinking back to the bonding section where atoms like to bond to other atoms in order to be stable. Well, these particular 7 molecules are very unstable when they're by themselves. So these tend to come in pairs. And these 7 diatomic molecules actually make a number 7 in the periodic table. So it's your halogens going down over to nitrogen. And of course, like I said, there's always exceptions. So the one that's missing is hydrogen. Hydrogen is always a lone wolf. So it's a part of the 7, but it's off to the side. So when we're predicting the products of these reactions, we have to keep these in mind. If I have nitrogen by itself, it doesn't exist by itself. It likes to come in pairs. There's 2 more that I want you to take note of, and it's actually sulfur right here. And I also have phosphorus. Phosphorus always comes in groups of 4. So P4. I don't know why, it just doesn't like to be by itself. It doesn't like to be in pairs. It always comes in 4. Something else you should note is sulfur. Generally speaking, sulfur likes to come in 8. So I always say sulfur's a tribe, right? It doesn't like to live alone. It likes to travel in a group. So other than the phosphorus coming in groups of 4 and your sulfurs coming in groups of 8, you can remember the diatomic molecules by just remembering that they make a 7 in the periodic table. Or the way I was taught this was by memorizing Bofinch. And I don't know why my chemistry teacher in high school liked to use Bofinch, but that was what he liked to use. So bromine always comes in pairs, Br2. Oxygen always comes in pairs, fluorine, iodine, nitrogen, chlorine always comes in pairs, and hydrogen. So if you remember Bofinch, and as long as you know that your halogens are included in there, you'll remember that all of those atoms are diatomic. Di meaning 2, of course, atoms. 2 atoms come together to form molecules. The first type of reaction is a synthesis reaction. And a synthesis reaction is when 2 or more compounds combine to form something new. We have 2 relatively simple compounds or elements, and they're combining to form something that wasn't there previously. And the very basic general equation for that is this right here. So A plus X yields AX. We're synthesizing something totally new. I'm taking A plus X and combining them together and producing a compound in which A is now bonded to X. That is a synthesis reaction. And here's some examples. So if I have magnesium bonded to oxygen, those 2 elements combine to form a new compound. In this case, which is magnesium oxide, MgO. And of course, you would have to balance that equation. Sodium combines with chlorine. I form sodium chloride. And again, double check for your diatomics. So notice that there's a 2 after oxygen here. That's because oxygen doesn't like to be by itself. When it's in its elemental form, when it's just oxygen, it likes to be in pairs, which is why we put that 2 on the outside of it. Same thing for chlorine. Chlorine doesn't like to be by itself. Here, it's not by itself. It's bonded to sodium, so it's okay. Only when it's alone. And here's another example. We can also do these with metal hydroxides or metal carbonates. So in order to produce either one of those, we have to start off with more simple compounds. So in this case, a metal oxide and water, they come together and they produce one final product of calcium hydroxide. So notice that for each of these samples, two substances become one. Two becomes one, two becomes one. That is a synthesis reaction. And there are a variety of steps that you need to take in order to predict the products for a synthesis reaction. So here they are. They're not in your notes, but I did attach for you these on a separate sheet of paper for you to reference. You should not have to reference these throughout the class. You should not have to reference these on your Chemistry 1 exam. You should become very comfortable with predicting the products for synthesis reactions. Therefore, what I would like to do is do these 5 together. So let's do those in the notes. So sample problem 11, let's go ahead and predict the product for each of these synthesis reactions. So you do have this predicting products cheat sheet that I gave to you, and I'm going to be referencing this kind of as we go through it. So for each of these, so we're going to follow this first step here. Identify the charge when each element forms an ion. So I'm going to go ahead and do this in pencil, actually, and I'm just going to write those charges on top of each of these elements. So if you look at that list of common ions, you'll see that potassium will always have a charge of +1, and fluorine will have a charge of -1. So you're just identifying what those are by looking at the list of common ions. If I had one here with me, I would show you, but for now you'll just have to trust me and look at that list. So we did step 1. The second step is write the elements as a compound with the cation first. And remember, the cation is the positively charged ion, so we can make a note of that here. The cation is always the positively charged ion. So write the elements as a compound with the cation first. So we're going to write potassium as my first element, and I'm going to write fluoride or fluorine after that. And you're going to write this as a compound, and it says, using the charges, write the correct formula for the new compound. So we're not bringing this 2 over from fluorine. The reason fluorine has a 2 here is because fluorine is one of our 7 diatomics. It doesn't like to be by itself. However, here, fluorine is not by itself. So you don't have to bring that 2 over. All you need to do is to cross over the charges just like you're writing a formula. Potassium has a charge of +1, and fluorine has a charge of -1. So there's our final formula. It happens to just be Kf. I'm going to erase all of that stuff just so it looks a little bit cleaner. So to balance this guy, looks like I would need a 2, a 1, and a 2. Let's try the next one. We're going to start from step 1. Identify the charge when each element forms an ion. Look at that list of common ions. Lithium is +1 and nitrogen is -3. Second step, write the elements as a compound with the cation. So let's go ahead and combine lithium and nitrogen. And step 3 says to actually make the new compound. So lithium has a charge of +1. That 1's going to come down here, but I'm not going to include that because it's always implied that it's there. And nitrogen has a charge of 3. So my formula is Li3N. Erase those. And again, notice I didn't bring that 2 over for nitrogen because here nitrogen is by itself. So it wants to be in pairs. Here nitrogen is not by itself. It's bonded to lithium, so it's happy. You don't need to make it a diatomic there. And when I balance this, There's my subscripts. You try C. So there's your answer there. Be careful, because in this case, your anion is actually listed first. And just because the anion's listed first doesn't mean that it goes first in the formula. Your cation, the positively charged ion, always has to come first. Aluminum is +3, so therefore that's first in the final formula. These next two are a little bit different. So in this case, you'll notice I don't have two elements that are combining, but I have two compounds. So this is my metal oxide, and I'm bonding that to water. So if I look back at my chart, a metal oxide that reacts with water will yield a metal hydroxide. And hydroxide, if you look on that list of common ions, has an OH with a -1 charge. So I have to combine the metal with the hydroxide ion. And of course, the only metal in this whole reaction is calcium. And calcium has a +2 charge. So at this point, you would write the formula. And when I write my formula here, that 2 will become the subscript after the hydroxide ion. And notice that that whole hydroxide ion is in parentheses there. And once you're done with that, you can just balance this. And actually, this one is already balanced. I have 1 calcium as in my reactants, 1 in my products, in my reactants, and 2 in my products. Be careful, you do have oxygen in both reactants, and 2 hydrogens and 2 hydrogens. I want you to try E. So E is you have a metal oxide bonding to carbon dioxide to produce a metal carbonate. See if you can do that one. So carbonate is the CO3 group with a -2 charge. So in this case, your potassium ion will combine with the carbonate ion to produce potassium carbonate, which is K2CO3. And that's it for synthesis reactions. Let's do decomposition next. Decomposition reactions are next. And when I think of something decomposing, I think of it breaking apart. And that's exactly what decomposition reactions do. They break apart. And this is a single compound that's going to break down and produce 2 or more simpler substances. Typically, for us, we're going to see that decomposition reactions are going to produce just 2 final products. And your general equation is just the opposite of synthesis. So AX, they're bonded together, those elements then separate. Typically, however, these reactions aren't going to happen on their own. You generally need some type of driving force for these to happen. So 2 of the best driving forces that we can have would be using an electric current, such as electrolysis, or you can use heat to decompose certain compounds as well. Couple of examples. So water, you can actually run an electric current through, and you could separate water into its components that way, so into hydrogen and oxygen gas. We also have diphosphorus trioxide. That can break down into its constituent elements. Notice phosphorus does have a P4 after that because they don't come in pairs. They like to come in groups of 4. And we can also have a more complex compound that breaks down into 2 more simple compounds. And just like synthesis reactions where we can produce a metal carbonate or a metal hydroxide from water or carbon dioxide or a metal oxide, you can also decompose those in the same exact way. So in this case, I have a metal carbonate is decomposing into carbon dioxide as well as the metal oxide. I actually think decomposition reactions are the easiest to predict for because all you need to do is just separate the elements in the compound, check for diatomic molecules. So if any of your Bofinch atoms are there, you throw a 2 after it, or if it's phosphorus or sulfur, you add either the 4 or the 8, and then you balance it. Pretty simple. And then there's those 2, of course, like we said, to watch out for. So we have metal hydroxides and we also have metal carbonates. Let's now get some practice with these in sample problem 12.
So I think decomposition are actually some of the easiest ones to do. In fact, I think they're easier than synthesis because you don't have to think about switching any charges. So predict the products for the following decomposition reactions. Again, I'm just going to reference this predicting products cheat sheet here. So we're going to focus on this first one here, total or complete decomposition. So the first step is to separate the elements in the compound. So for A, I have aluminum oxide. And of course, we have no option but to separate aluminum from oxygen. So step 1 is now done. Step 2 says, look for diatomic elements and add a subscript of 2 as needed. You also should check for phosphorus, which comes in the groups of 4, and you should check for sulfurs, which comes in the group of 8. So make a note of that on your paper. And if you remember, oxygen is a diatomic, so I'm going to put a 2 after that. Aluminum is happy being by itself, so I don't have to put any subscripts there. And then the last step is just to balance. Like I said, I do think that these ones are pretty darn easy to separate or to predict the products for. So it looks like I needed 2, 4, and 3. Let's try B. So again, separate the elements in the compound, step 1. So I have NH3, which is ammonia. Separate that into its elements. Step 2 says to check for diatomics, and actually both of those are diatomic. So you put a 2 after those. And then I balance. 2, 1, 3. You try C, so pause the video and write the products for C. And there you have that one. Be careful, sulfur is one of those ones that comes in groups of 8. So you do want to write S8 as one of your products. And your coefficients would be 8, 16, and 1. It also does not matter the order in which you write the products. You can write sulfur first and silver second. The only time it matters is when you're writing a brand new compound. D, so this looks similar to those synthesis ones that we talked about. So this is when you have a compound that's decomposing into a more simple compound. And for D, I have a metal carbonate. So metal carbonates decompose into metal oxides and carbon dioxide. So one of my products is going to be a metal oxide, which in this case it's zinc oxide. So I do have to actually write a formula here. Zinc has a charge of +2 and oxygen is -2. So actually those will cancel each other out. And my other product is carbon dioxide, CO2. And then you would just balance it from there. All of your coefficients are 1. Try to do E. So E is using this first one right here. Metal hydroxides decompose into metal oxides and water. And there's your final equation there. So in this case, I did choose for copper to have a +2 charge in my metal oxide, only because copper has a +2 charge in my metal hydroxide. Personally, I just like to keep whatever charge the transition metal had on my reactant side. I think it keeps it easier to follow that way. And that's it for decomposition. Like I said, other than D and E, I think problems that are similar to A, B, and C, which are the ones you'll see 95% of the time, that they are very easy to predict the products for. You just have to keep those diatomic molecules and your phosphorus and your sulfurs in mind. Let's do a single replacement next.
The next type of reaction is a single replacement, and single replacement reactions are when one element replaces a similar element in a compound. And when I say similar, we mean either positive for positive or we mean negative for negative. So positive replaces positive in a single replacement reaction and negative replaces negative. So your general equation, there's 2 of them really. It depends on if you're switching the positives or the negatives. In this case, A plus BX will yield AX plus B. Notice A and B are considered similar because they're both at the beginning of the alphabet. So A and B are switching places. A combines with X and B isolates out. Here's your second general equation. In this case, we are switching Y and X, and they're considered similar because they're both at the end of the alphabet. So Y is replacing X, and it's combining with B and isolating X on the outside. Some examples. Actually, the first lab we're going to do is a single replacement lab. It kind of gets you into the swing of writing in the lab notebook. So you'll do lots of single replacement reactions with the activity series. Magnesium reacts with hydrochloric acid to produce hydrogen and magnesium chloride. Magnesium has an overall charge of +2 when it's in a compound, and hydrogen has a charge of +1. So because magnesium and hydrogen both have positive charges, they have the ability to replace one another in the final products. So magnesium and hydrogen are switching places, and magnesium combines with chlorine on the opposite side, and hydrogen isolates itself out. You do have to check your charges here and add diatomics where necessary. You can't combine magnesium and hydrogen because they're both positives, and positives don't attract one another. We always have to have a positive bonded to a negative. Here's another example where you are switching your negatives or your anions. So chlorine, a halogen, is going to replace the other halogen, bromine, in this example. So chlorine and bromine switch places, and bromine isolates itself out, and that chlorine combines to potassium. This one looks scary, but it's not. The only reason why it looks that way is because you have a polyatomic ion in there. So aluminum and lead, both metals, both have a positive charge. Therefore, they are going to switch places. When they do, you will form the two products of lead, and you will have aluminum nitrate, of course, with the proper subscripts that were brought down from the charges. And here's some steps on how to predict the products for the single replacement reaction. Again, you have that handout with those on it. And what I'm going to do is walk you through each of these steps when we do those sample problems together. The only thing is, if you are looking at this at all, you'll see that step 3 says check the activity series to determine if the element has the ability to replace. These reactions will not always occur, and we can tell if they are going to happen or not by looking at something called the activity series. And this is an example of an activity series, and I actually put this in your notes as well. So what is the activity series? It's a list of elements that's organized to the ease with which the elements undergo chemical reactions. So your elements towards the top of this activity series are very, very reactive. So these are your alkali metals and your alkaline earth metals all the way over to the left side of the periodic table. Those elements have very low electronegativities, very low ionization energies. They want to get rid of their electrons very easily. Therefore, they are the most active, or they are the most reactive. They want to be in a compound. They don't like to be by themselves. As opposed to your elements on the bottom, these are the least active. These elements like to be by themselves. For example, you have silver, platinum, and gold. That's why they are precious metals, because they don't tarnish, they don't react over time. They like to be by themselves. So those elements are not going to replace other elements very easily to form compounds. These elements towards the top like to be in compounds, whereas these ones at the bottom do not. So when we're doing our single replacement reactions, we need to check the activity series to make sure that our lone element is more active than the element it wants to replace. The lone element has to want to be in a compound more than the element it wants to replace. And you could do that by checking this. So again, your most active or your most reactive elements are at the top, whereas your least active metals or elements are at the bottom. You do have a little baby activity series here. Those are just for your halogens. So if you are replacing anion for anion, you'll have to check that little tiny baby activity series to see if that particular reaction will occur. So fluorine wants to be in compounds much more than iodine does. It's the same exact thing, but we're just dealing with our halogens in that case. Let's get some practice with that and do sample problem 13.
So let's try these single replacement reactions. So sample problem 13, predict the products for each of those. And there's a little bit more steps for this, but it's not something that is totally undoable. So like I said, we're going to do probably the first two together, and then I'll have you do the rest of these on your own. So number one, identify the single element and the charge it will form when it's an ion. So aluminum, in this case, happens to be the single element, and aluminum will form a charge of +3. Step 2, determine which element it will replace. So remember, positive replaces positive and negative replaces negative. So aluminum wants to replace the positively charged ion in the compound. It wants to replace it, not bond to that. Because remember, positives and positives don't attract. There always has to be a positive and a negative. So aluminum is going to want to trade places with tin. And tin has a +4 charge in this example. And we know it's 4 because that 4 that belongs to fluorine must mean that it's the charge on tin, whereas fluorine is -1. So aluminum and tin will want to trade places. However, if we look at step 3, we have to check the activity series and determine, does aluminum actually have the ability to replace? Is aluminum more active than tin on the activity series? So I have an activity series handy here. And remember, your most active elements are here towards the top. So your alkali metals and your alkaline earth metals, and then you have a lot of your metals down to here. So aluminum has to be higher than tin on the activity series. Aluminum has to be more active. Aluminum has to want to be in a compound more than tin. These elements down at the bottom like to be by themselves. They're very happy by themselves. That's why they're transition metals. They really don't care to exchange electrons as much as these ones at the top do. And if I notice, here's aluminum and here's tin. Aluminum is, in fact, more active than tin. So yes, this reaction will occur because aluminum has the ability to replace tin. So, since we've determined that, which is actually steps 3 and 4, if the activity of the lone element is lower, then there is no reaction. Aluminum was higher than tin, so this will occur. If the reaction is possible, exchange the element with the corresponding element and write the replaced element by itself. So, aluminum is going to want to combine with fluorine, and tin is going to isolate itself out. What we have to do is exchange our charges to make sure we have the correct formulas. So aluminum has a charge of +3, so that 3 is going to come down by fluorine. And fluorine has a charge of -1. Tin is not a diatomic, so you leave it as it is. You don't need to put anything after that. I'm going to erase all this other stuff that I put in there just so it looks a little bit cleaner. And then the last step, as always, is to balance. So I like to balance my fluorines first, just because it's easier to find the least common multiple there, because I can throw any number in front of these two elements. 4 in front of aluminum, 3 in front of tin. And just like with your decomposition reactions, it doesn't matter the order in which you write the products. You can write tin first and then aluminum fluoride. Doesn't matter. Let's try B. So, checking from the top here, identify the single element and the charge it will form. So, potassium is the single element here, and that will have a charge of +1. And we have to identify which one of these two elements will it want to replace. Again, positive replaces positive. So potassium is going to want to replace chromium, because chromium in this compound is also a positive charge, and more specifically, it's +3. Oxygen has my -2. However, we have to see, does potassium have the ability to replace chromium? So potassium has to be higher on the activity series. So here's potassium, and chromium is all the way down here. Not all the way down, but about halfway down. So potassium is more active. Potassium does want to replace chromium. Chromium is much happier being by itself. These elements down towards the bottom like being alone, whereas these ones at the top like to be in compounds because they have 1 or 2 valence electrons. They want to get rid of those valence electrons, so they'll do just about anything in order to do that. So this reaction will proceed, and I can then write the products. So potassium is going to combine with oxygen, because again, it's always positive, has to combine with negative. Write the formula, and I'll isolate chromium. Let's erase all of this stuff here that I just wrote. And then we will balance. One of my other pro tips for balancing, I always start off with a compound that has a lot of subscripts. So here I'm going to start balancing these guys, just because there's a lot of values there, and I like to kind of get that out of the way first. So it looks like I need a 3 and a 1. Oxygen's done. 2 chromiums is done. 6 potassiums is done there. I want you to try the rest of these, and before you do that, just remember C and E, you're actually replacing halogens for halogens, and there is that little tiny baby activity series off to this side. So remember that you're not going to find those halogens in this section here, because this is your activity of metals. Therefore, you have to look at the halogen nonmetal side for that, for D, C, and E. If there is no reaction for one of them, which I believe you will find, you can just write NR as your final product. So anyway, give those next 3 a try. So there's your answers there. So like I just mentioned, for C and E, you did have to check that little baby activity series with your halogen nonmetals on it. So chlorine has to be more active than iodine, because chlorine's going to want to replace the negative since it itself is a negative. And if I look, chlorine is in fact more active than iodine, so this reaction will occur. D, on the other hand, zinc is not active enough to replace aluminum. Zinc is happier being by itself than aluminum is being by itself. So therefore, zinc's going to stay isolated. When that happens, you don't have to predict the products. You can just write NR for that. And NR, of course, stands for no reaction. And E is very similar to C, except you do have a polyatomic cation there that you have to account for. But otherwise, I think as long as you follow each of these steps and you check that activity series, then you should be more than good for predicting the products. Let's go ahead and do double replacement next.
So now let's talk about double replacement reactions, which, you guessed it, doubly replace elements in a compound. We're not just forming one new compound, we are going to form two new compounds. So in this case, ions of two compounds exchange places to form two totally new compounds. And your general equation looks a little something like this. So AX plus BY yields AY plus BX. So notice that Y and X are changing places here, and that's because they are both negatively charged. Again, I can't put A and B together because they're similar. They both have positive charges. They don't want to be together. So you're replacing X and Y with one another. A is combining with Y to form one new compound, and B is combining with X to form that second new compound. So AX plus BY yields AY plus BX. And it doesn't matter the order that the products go in. You can also have BX plus AY. Same exact thing, doesn't matter. As long as the two products are written correctly, then I'm happy. Some examples. So potassium iodide reacts with lead 2 nitrate. And notice in this case, you are replacing anion for anion, so negative for negative. This nitrate and this iodine are changing places. So lead is combining with iodine, and we're producing lead 2 iodide as a result, in addition to potassium nitrate. So this ion right here combined with that ion right there, and lead combined with iodine. I had two compounds as my reactants, and I formed two new products after that double replacement reaction. Notice there's some other symbols there. We're going to talk about those in a second. Same thing here. I have two compounds as reactants. Those anions or those cations are going to switch places, positives for positives. So iron and hydrogen are switching places here. And iron combines with chlorine to produce this one final product. And hydrogen combines with sulfur to produce this second final product. And of course, you would balance that when you're done. And then the last one I have is hydrochloric acid and sodium hydroxide, the same exact thing. We're switching cation for cation or anion for anion to produce each of those two final products. And there's, of course, some steps on how to predict the products for these. And if we look here, we do have to check the solubility chart. So rule 3 does say to check that. Well, what the heck does that mean? Your solubility chart will tell you whether or not you are producing a solid precipitate, if you are producing a solid material as a result of combining these two compounds together. So what this reaction is stating is that aqueous potassium iodide, so aqueous means it's a water solution, it's dissolved in water. I have an aqueous solution of potassium iodide combining with an aqueous solution of lead 2 nitrate, and we're producing solid lead 2 iodide, which is this pretty yellow compound you see in the test tube, in addition to potassium nitrate, which is still dissolved in the water. We are able to predict whether or not we produce solid materials as a result of reactions. And we can do that by looking at a solubility chart. So all of your cations are going down this left-hand side. So I'll put a plus sign here for cations. And all of your anions are going across. And if you just find the combination of cations to anions, you can then determine, is that compound going to be a solid, yes or no? For example, if I look up sodium chloride, so I want to know, is sodium chloride soluble or does it dissolve in water? I would go down here and I would find sodium, and then I would go across until I find chloride, and chloride is right here. So there's an S. Now, S doesn't mean solid. You have to look at the key to say what S stands for. And S means that it is soluble in water. So soluble in water. That means that it dissolves in water. So you would have an AQ next to sodium chloride. Sodium chloride dissolves in water. Therefore, we say that its state of matter is aqueous. Anything that is not an S will always be a solid. So it's kind of backwards. When you see S on the solubility chart, it's aqueous. But if there is no S, it's a solid. So unfortunately, that's the way it works for these. That's my kind of rule of thumb with them. Anytime you see S on here, it stands for soluble, and anything else would be a solid material. Let's do sample problem 14. Almost done.
So sample problem 14, predict the products for the following double replacement reactions, and then we'll balance. So just like before, let's use our cheat sheet here for how to predict the products. So step 1, replace cation for cation or anion for anion in the compounds. So I usually like to switch cation for cation, and I say that, but I'll probably switch anion for anion in the next one. So it doesn't matter. You're just switching positive for positive or negative for negative. So I'm going to switch barium and sodium. And then I'm going to write the new compounds, but I have to switch over those charges. So sodium now is going to combine with chlorine. Don't bring over those subscripts, though, with these that are within these other compounds. You don't need to bring this 2. You're just bringing the element. The reason why I have a 2 after this chlorine is because it's bonded to barium. But here, actually, this is a 1-to-1 ratio. So you don't need to bring the 2. So there's my first product. And I'm going to combine barium with carbonate. Barium has an overall charge of +2. Carbonate is -2. So actually those will cancel one another out. The next step is to check the states for the new compounds using the solubility chart. If both products are aqueous, then there is no reaction. If a solid, liquid, or gas is formed, then the reaction will take place. So let's check the solubility chart for both of these, because double replacement reactions, when I have 2 aqueous solutions, which of course means that it's just, there's no solid particles in there, they're just dissolved in water. Sometimes you'll have a solid precipitate that's formed. So we want to know, when I combine those 2 solutions together, will I form a solid material? And we can tell by using this solubility chart. So off on this left-hand side, I have all the cations listed. And going across the top, I have anions. So we're going to match up sodium and chloride. So sodium, it's kind of cut off here, but you get the idea. And chloride is this one right here. And in the note section, I mentioned that S does not stand for solid, but S stands for soluble in water. And soluble means that it dissolves. So NaCl would be aqueous in solution that dissolves in water. Let's check barium chloride. So here's barium carbonate, I'm sorry. Here's barium and here's carbonate. And notice there is a P. And P at the bottom says partially soluble in water. So that means some of it's going to dissolve, which means that we will see that there is in fact a solid precipitate that's formed. Anywhere you see an S on this solubility chart means that it's going to be aqueous in solution. It dissolves in water. Anywhere where there's not an S, you're going to write an S because it's a solid. So it's backwards in that case. So we actually will see a reaction here because I do have a solid precipitate that's formed. And then, of course, like always, let's just balance. So I'm going to throw a 2 in front of sodium chloride. And then we're done there. Let's try G. It should be, it happens. So I'm going to switch magnesium and silver. And let's go ahead and predict the products there. So silver is going to combine with iodine. Silver is +1. Iodine is -1, so that is actually good the way it's written. And magnesium is going to combine with nitrate. So magnesium, nitrate. Magnesium has a charge of +2, so I have 2 nitrate groups, and nitrate has a charge of -1. So we don't have to write anything there. Next step is to check the solubility chart. So silver iodide. Silver is down here. Let's find iodide. Sometimes it's a little tricky. Capital letter I at where those two intersect. And again, because there's no S there, that means that it is an S. Silver iodide will produce a solid precipitate when those ions come into contact with one another. And magnesium nitrate, going to be somewhere down here. That is an S, and S stands for soluble. So I'm going to write AQ. So for this one, yes, we will see a reaction in our test tube because we have a solid precipitate. If I have 2 aqueous products, you will not see a solid precipitate. And then I balance. It does not matter the order in which you write those products. As long as both of those products are there, then you're good. I want you to try H, I, and J doing what we just did, writing those correct formulas for products, predicting the solubility, and then balancing. And there's your answers for those 3. Check for I. So I, we're producing water, which is hydrogen hydroxide. So we don't say that water dissolves in water. That sounds silly. So rather than saying that water is aqueous, what we say instead is that water is a liquid. If I look on this paper right here, this is one exception to this rule. So hydrogen hydroxide, you'll see that there is a dash there. That is not going to be a solid. Hydrogen hydroxide is a liquid. That is water. That's a crazy sounding name for water. So in this case, we would actually form a reaction here. And this is not a precipitation type of reaction. This is what we call a neutralization reaction. We have a strong acid reacting with a strong base, and that gives us water and a salt. One of the reasons why I'm doing this review as videos is so that way later on in the year we can talk more about things that normally we don't have time to talk about. So this would be one of those things that I would hope to get into, is the difference between neutralization reactions versus precipitation reactions versus something else called a redox reaction. But there's your examples there for double replacement. Let's get into the last reaction and do combustion.
And the last type of reaction is a combustion reaction. And combustion reactions, I think, are also very easy, up there with decomposition. They're easy except when you balance them. These can be tricky to balance. But these are a reaction of oxygen gas with all types of substances. Anytime you combine oxygen with something else, that's usually a combustion reaction. And there's quite a few general equations, actually. Here is the most common type of combustion reaction that you'll see. So you have some hydrocarbon, which is carbon bonded to hydrogen in some ratio, combining with oxygen gas. And when you do that, you are producing 2 products and 2 products only. You're producing carbon dioxide and water. That's it. Anytime you have a complete combustion reaction, those are the products. Now, sometimes you might have an incomplete combustion reaction, and incomplete has the same 2 reactants, But sometimes there's not enough oxygen getting to that fuel source. There's not enough oxygen getting to that hydrocarbon, that compounds that contains both carbon and hydrogen. And when that happens, not only do you produce carbon dioxide and water, like I just underlined there, but you also produce solid carbon and you produce carbon monoxide. Now you see incomplete combustion a lot, and anytime there is like a black soot on something, or when you see those trucks driving on the highway and they have like those big black clouds of smoke, that is there as a result of incomplete combustion. That is carbon that is coming off of that reaction. So you see incomplete combustion a lot, or at least I see it a lot with candles. So if that candle wick is really, really tall, it'll start to produce a black soot around the inside of that. And that's because there's not enough oxygen getting in order to completely combust the candle wick. You might also see this in a fireplace. If you have a lot of soot build up within a fireplace, it's like a black film. That's also incomplete combustion. That's all carbon buildup right there. And then, of course, there's just the very basic type of combustion reaction, which is just any element combining with oxygen to produce some combination of that element with oxygen. This is the most common one that you are going to see is complete combustion. You need to know that a hydrocarbon plus oxygen yields carbon dioxide and water. Here's an example of each one. Like I said, I really think the hardest part about these is balancing them, which we're going to do some practice with in this last section. There they are. There's your two products, CO2 and H2O, balanced properly. Here's an example of one with incomplete combustion. I will tell you if it's incomplete combustion. And to be honest, you rarely ever see incomplete combustion questions. I just like to put it there because I think it's applicable to stuff we see in real life. We see incomplete combustion a lot. And then, of course, we have this last general combustion reaction, which is also a synthesis reaction. So as we start diving deeper into Chem 2, and if you decide to take AP chemistry, you'll see that there's some overlap with the different types of reactions. In this case, this combustion reaction down here could also be considered a synthesis reaction. It doesn't matter. Sometimes you have a little bit of overlap. And of course, to predict the products, you really don't even have to predict them because the products, 95% of the time, will always be carbon dioxide and water. So like it says in the directions, this will be given to you in an equation. So there's your products for complete, there's your products for incomplete, and then you balance it. Last one, let's dive in and do sample problem 15, and then we're done with the review.
So sample problem 15, predict the products for the following combustion reactions. This one is very easy to predict the products for because most of the time your products are going to be carbon dioxide and water. And the only time it's not is when you have an incomplete combustion. And in that case, you would have two additional products. You would have carbon monoxide and carbon. So, and I will tell you if it is incomplete. So that's what this INC means. It's that it is in fact an incomplete combustion. So for these first four, however, these are CO2 and H2O. So I can just write those as products. And then for this last one, you can write CO2 plus H2O, but it is incomplete. So I have those two additional products, carbon monoxide and carbon. I think with these, the hardest part is balancing them. So we're just going to balance these 5 together as we go along. One of my tricks is to always balance carbon first for these because you only have carbon in one product and one reactant. So for K, I have 1 carbon here and I have 1 carbon there. So that's good. Put a little check mark above that. 4 hydrogens. Looks like I need 4 here. So I'll put a 2 in front of water. And I have 2 oxygens plus another 2 from the 2 water molecules is 4. Looks like I need a 2 above the oxygen. L, same exact thing. Let's start off with carbon. So I have 3 and 1. So I'll flip those. Hydrogens, looks like I have 8 in propane. That's this C3H8. And I need 8 over here. So I need 4 water molecules to do that. 6 total oxygens here, plus another 4 gives me 10. Remember, don't put a 10 here, but you need how many groups of 2 to give you 10? You should have 5. For the next one, let's see, start off with carbon again. So I have 1 and 4. Hydrogen, so I have 10. Looks like 5 times 2 is 10. But watch this. 4 times 2 is 8, plus another 5 gives me 13. Look what happens here. I can't have 6.5 oxygen molecules. So what I have to do, and you're going to see this sometimes with combustion reactions, is you have to multiply all coefficients by 2, just like you were doing when in some of those balancing problems. N, let's start off with carbon. And if you notice, I have oxygen in every single reactant and product here, so you have to be careful. So I have 1 and 6. 10 hydrogens. I need 10 here, so I'll put a 5. Now let's balance our oxygens. So on my product side, I have 12 plus another 5 gives me 17. So I need 17 here, but look, I already have 5 in my other reactant. So really you only need 12 here. 6 times 2 is 12. So just make sure you're double and even triple checking to make sure that you have them all balanced out in the end. Oh, so this one you can balance probably 100 different ways. So what I'm going to do first is I'm going to just double my number of carbons in my reactants. And the reason why is because I have 1, 2, 3 carbons in my products. So I'm just going to add 1 there. Just because then I can kind of manipulate what I would like to work with. Something else I notice is my number of oxygens. So I need to have an even number of oxygens because I have my oxygen in pairs as my other reactant. So right now I have 2 plus 1 gives me 4. So that works out. But let's just go back and look at hydrogen first before I start to do that. So 2 groups of 2 gives me 4 hydrogens total. Let's go ahead and put 2 groups there. Hydrogens are done. That's the only one that's done at this point. This one takes a little bit of extra work, which is why I'm kind of going back and forth. Let's check oxygens again, just because we want that to be, we need it to be even, like I said, and right now it's not even. So 2 plus another 2 gives me 4, plus another 1 gives me 5. Well, I need to have an even number, so I'm going to double this one. So I have 6 total. 1, 2, 3, 4, 5, 6. Looks like I need 3. And let's just check our carbons. 4 in my reactant side. 1, 2, 3, 4 in my product side. This equation is now balanced. As always, if you have any questions, this is probably the trickiest part of everything we've been doing, just because I know for me, some of you guys, we didn't get this far, especially with the quarantine. So you might need some extra practice with this, and that's okay. We're going to do a couple of labs with the types of reactions when you come into Chem 2. But by all means, please email me with questions, stop by and see me, ask me in class because we're going to be together soon. Do not be afraid to learn this material, and I'm here for you along the way. Anyway, I'm going to sign off now, so I hope you guys have a great day, and I look forward to seeing you in class very soon. Bye.